Okay, here we go. Let's see where the kinematic equations actually come from, at least not thoroughly, but have a pretty good idea of it. So for everyone who's watching this going, actually, what you've done there is not mathematically appropriate, it's still like 90% of what we're looking for, and it gets across the point and how to work with this. Let's start off with a definition. One of the definitions that I gave you earlier is that the acceleration is defined to be the derivative of the velocity with respect to time. Another one that we have, and we'll work with it here in just a little bit, is that the velocity is defined to be the derivative of our position with respect to time. Now, if we're taking derivatives with respect to time, then that means that our velocity is a function of time, so that we can take a derivative of it. If it is not a function of time, then it would be a constant, and our acceleration would be 0. We'll take a look at that at one point. Same thing with our position. If our position is constant, then our velocity would be 0. But if our position changes with time, then we can take the derivative and we'd be able to find the velocity function. All right, we're going to start with the acceleration one, because what I want to do is I want to come up with some of the kinematic equations that we work with. So let's start with this statement by itself. And there's one other thing that I'm going to bring up. I talked about how these may or may not, they should be, but they might not be a function of time. So I'm going to bring in something. I'm going to assume the following. Assume that your acceleration is not a function of time. Or said differently, assume that acceleration is constant. I told you I want us to see where our kinematic equations come from. I told you, and this is fundamentally important, on that kinematic equation sheet that I give you, this one here, that you're supposed to add in that these only apply when acceleration is constant. You're seeing right here that I'm starting off assuming, for what we're working with, that the acceleration is going to be constant. All right, here we go. Acceleration is constant. So I'm going to take the equation that I have above. My acceleration is defined as, although in this case I'm probably just going to write it as a regular equal sign because we're going to do math, dv dt. Great. Now I'm going to do the thing that we talked about before. I'm going to do separation of variables, dt. I get the following. I'm going to flip the sides here. dv, I'm going to get a little lazy with my vector signs, but we do know that they are vectors. dv equals our acceleration dt. Now, I don't want an infinitely small piece of my velocity. I actually want to know what my full velocity function is. So here's what I'm going to do. I'm going to integrate that so I can add up all the infinitely small pieces of velocity. And here's where I can bring in some of my limits of integration. I'm going to start from, let's say, v0, my initial velocity, to v final, my final velocity, or my velocity at some time t. I'm going to call that vt. Technically, I shouldn't be integrating and using the limits of integration with the same variable. That's some calculus stuff, but we're going to ignore that. I'm going to integrate, I'm going to add up all these little tiny pieces of v, the velocity, to start from the initial velocity and go to my final velocity at some time t. I'm going to call that vt. To do that, I need to integrate my acceleration, dt, from time equals 0. Now we're looking at time, so I'm going time at the very beginning is time 0, and I'm going to go up to some time t. Now, technically, I shouldn't use the limit of integration and the variable to be the same thing, but please forgive me, math professors. I'm going to break that small rule just for simplicity. All right. Well, when we integrate this, I didn't fully show everything that we needed on that, but I just kind of showed you what you can work with on the integral. This may be a little bit ahead of where you're at. But this evaluates to, well, dv simply adds up to v, and I'm going to evaluate it from v naught to v as a function of time, or v final, whatever my speed is at the, velocity, is at the end of the interval I'm looking at. So dv, I add all the little d's, the small pieces up, and I will get v, and then now I'm going to evaluate it from here to here. This equals, let's see, a being a constant can come out of the integral. So I get a times the integral from 0 to t of dt. Well, that becomes, I have v evaluated from v naught to v final equals my acceleration times t, where t is evaluated from 0 to t. What we mean by evaluated is we take the upper limit minus the lower limit. So what this is going to become is v final minus v initial equals a times t minus a times 0. Well, this term just disappears into 0. And we can see by assuming that the acceleration is a constant, it comes out of my integral, and we get the following. V final minus v initial equals at. I now add my velocity, my initial velocity, I should say, over to the other side, and we have the first equation on your equation sheet. This is where that equation comes from. It comes from the definition of the acceleration. It is defined to be the time derivative of the velocity function. If we assume that the acceleration is constant, we will end up with this equation. Now, this only holds if the acceleration is constant. That was an assumption I made to come up with this. We're going to check a couple of the others, see where the other equations come from, and then we'll finish this up by looking at an instance where the acceleration will not be constant and how we could work with that. First of the kinematic equations has been achieved. Now, another way that I could write this is my v final could also be treated as v at some time t equals my initial velocity plus a times t. My v final could be wherever I put t in for, so t for 3 seconds. That would be my final velocity. That tells me my velocity here. Great. I do not need to add in an unknown constant on this because I did what's called a finite integral, which I didn't show you in the previous one. Again, some of this you're not going to be top-notch on until you've learned some of this in calculus class, or come speak to me outside of class. But we have limits of integration, which means we don't have to worry about the plus c. That will actually take care of that unknown constant that may or may not be there. Here's our equation. Great. Now I'm actually treating this where v of t this is a function of time. I put time in, my constant acceleration, and as long as I know my initial velocity, I can find what my final velocity will be at some time t. Now let's take a look at the other one that we mentioned. There's also this one, that the velocity is defined to be the time derivative of our position as a function of time. It's not a very good D. I'm going to do the same thing that we did with the other one. dt. These should be well-behaved functions, so I can actually do this, and I get the following. I get, let's see, we get dx equals v dt. I have an infinitely small piece of my position and an infinitely small piece of time, and they are related by my velocity. Again, rates of change. Now I'm going to go backwards away from the derivative. I'm going to do an integral. I'm going to do an integral here from my beginning position, x0, to my final position, x1. I'm going to integrate this. This is time, so we're going to go from time 0 to some time t. Great. Okay, well, dx just adds all the little pieces of x up, and we end up with the following. X evaluated from x0 to x final equals v. V is not constant, so I cannot simply bring it out of the equation. We're going off the assumption that our acceleration is constant, but if our acceleration is constant, then I can do the following. This is velocity as a function of time. Well, what did I finish up with here? My velocity is a function of time. And this is what the velocity will be as a function of time if acceleration is constant, so we're going to go ahead and use that. So instead of v, I can have velocity as a function of time is equal to this. My initial velocity plus my acceleration times my time, and that whole thing is my velocity as a function of time. If I want to find the velocity at any given time t, I put the time in here, and then it will tell me what the velocity is, assuming I know the acceleration and the initial velocity. All right. Great. So we've got x evaluated from x0 to x final equals the integral. I'm going to spread this out because I like doing this. v0 dt plus the integral from 0 to t of at dt. Now, one thing that I do want to remind you of is we're assuming that the acceleration is constant, which means the acceleration can come out of the integral. On top of that, v0 my initial velocity doesn't change. It's a number. We may not know it right offhand, just like we don't know the acceleration, but the initial velocity is however fast it's going at the very beginning, and for your problem, that is a constant. The velocity, as a function of time, that will change throughout the problem, but the initial velocity will stay the same, because that's how things were at the very beginning of the time period you're looking at. It's a constant, which means we get the following. X evaluated from x naught to x final equals v naught times the integral from 0 to t of dt plus a times the integral evaluated from 0 to t of t dt. I'm going to go ahead and fill this in. This may be a bit of a leap if you haven't had much calculus before. I'm going to fix this up. We're going to have x final, minus x initial equals v naught times, well, this is going to be t evaluated from 0 to t, plus this will be 1/2 a t squared evaluated from 0 to t. T would integrate to 1/2 t squared. Great. We don't need a plus c in here because we have finite integrals where we're actually giving, or definite integrals where we have our limits. Okay, so I'm going to clean this up a little bit. Real quick, final minus initial. I seem obsessed with that phrase in class. What was final minus initial again? Delta x. Many groups will actually use x final and x initial. To make things simpler for you all, we primarily deal in delta x, which is our displacement. All right, v naught times t minus 0 plus 1/2 a t squared minus 1/2 a 0 squared. The other terms disappear because of these zeros. We end up with delta x equals our initial velocity times time plus 1/2 a t squared. Here is the second equation on your equation sheet. This is where it comes from. Now, I did these in a logical order so that we could use the first one, the velocity as a function of time, so that we could actually derive this. But you'll remember that the only thing that we have used, other than a little bit of calculus knowledge, are these two definitions and the assumption that the acceleration is constant. Great. There are our first two equations. And once you have those, you're pretty well set, because what you can do at this point is you can start solving things in terms of one to find the other. So for instance, let's say that I want the third equation. The third equation has no initial velocity. So here's what I'm going to do. I have two equations. I've got v final equals v initial plus a t, and I've also got delta x equals v initial times time plus 1/2 a t squared. Here's what I'm going to do. I'm going to move this one around where I'm going to solve this so that I get the following. Double check this at home, but v naught will be equal to v final minus at. Well, if this is v naught, I can plug that right in there, and I get the following. I get delta x, because we know where both of these equations came from. We got them with calculus. Equals v final minus at times t plus 1/2 a t squared. All I've done is I've solved this equation for my initial velocity, and now I'm plugging that back in over here. Okay? Well, I get delta x equals v final times time minus at squared plus 1/2 at squared. You'll notice that I'm going to distribute this t. There's a t here, and then this t becomes a t squared. Well, I've got minus at squared plus 1/2 at squared, so what I'm going to end up with is minus 1/2 at squared. There's the third equation. Let's try a different one. Fourth equation, the one that doesn't have acceleration. Great. Let's go back to the first two equations that we had. We had v final equals v initial plus at, and we had delta x equals v initial times time plus 1/2 at squared. You can also use the one that we just finished up with, but now I'm going to try and get rid of acceleration, so I'm going to solve this one for acceleration. For forgive me for doing this in my head, v final minus v initial divided by time is going to be equal to my acceleration. Well, if that's my acceleration, I can plug it right in here, and we get the following. Delta x equals v naught times time plus 1/2 v final minus v initial divided by time times t squared. Let's clean this up a little bit. We've got divided by t and times t squared, so one of those cancels out. And we get the following. Delta x equals v initial times time plus 1/2 v1, v final times time, minus 1/2. Doing this correctly? I'm distributing the 1/2. Yep, v naught times time. It's a little bit of algebra here, but I have the initial velocity, v naught times time, minus 1/2 v naught times time. So I can clean this up. Delta x is equal to 1/2 v final times time plus 1/2 v naught times time. 1 minus 1/2 is positive 1/2. Bingo. Now, this is perfectly good, but I can factor the 1/2 over here, and I end up with the following. v1 plus v naught times time. I can also factor the t out there. Why am I doing that? I'm doing a little bit extra, but I'll be completely honest. It's to put it in exactly the form that we see it on the equation sheet. That's equation number 4. And for the last one, you've got an idea of exactly what we're doing now, but we're on a roll, so might as well finish this up. v final equals v initial plus at. And we've got delta x equals v naught times time plus 1/2 at squared. In this case, I want to get rid of t. Now this one's going to be a bit more of a pain, but let's see what we've got. So what I'm going to do is I'm going to rework this around, subtract that over, and divide by a. So I'll get v final minus v initial divided by the acceleration equals t. I then plug those in to here and here. There might be an easier way to do this using some of the other equations, but might as well go with what we've got. Delta x equals v naught times v final minus v initial divided by acceleration plus 1/2 acceleration times, oh dear lord, v1 minus v naught divided by acceleration quantity squared. Yep, we're going to have to clean this up a little bit. Okay. Okay, I'm going to spread this out some. It's going to be a bit of a mess, but we'll go ahead and play around with it. So I've got, let's see, I'm going to do 1 over a times the quantity of v final minus v naught, or multiplied by v naught. Both of these together, and I've moved the 1a out, minus v naught squared. That's this one times that one. Plus 1/2 a times the quantity of, I'm going to do v1 minus v naught quantity squared. I'm going to leave that like that for now, over a squared. Here's what I'm going to do. I'm going to multiply both sides by a. This term has a 1 over a, that term has a 1 over a, and I'm going to multiply this by a. I get the following. Acceleration times delta x equals, yeah, this is not terribly pleasant, but that's fine, v final minus, or times v initial minus v initial squared plus 1/2, well, v final minus v initial quantity squared, which if I FOIL those out, if you will, that'd be v final squared plus v initial squared minus 2 v1 v naught. If I'm not mistaken. I think that's right. Double check my math. Great. Sorry, that's 1/2 times this whole thing. Because it's 1/2 times that. Whew. This is getting fun, isn't it? Okay. Let's see. I've got a and delta x over here. We've got v final and v initial. Let's see, it's 1/2 times all of this. Let's clean that up. That's v final, v initial minus v naught squared plus the quantity of, I'm going to distribute the 1/2, so we've got v1 squared over 2 plus v naught squared over 2 minus v1 v naught. The 1/2 and the 2 cancel out. v1, v final, v naught minus V final, V naught, this minus and this actually cancel out, and we've got a lot better here. Let's see. Have I done this correctly? I certainly hope so. Okay, sorry about that. Turns out I'm just a crazy person, and I've been staring at this board entirely too long. Minus V naught squared, we could write this, in fact, let me clean it up. A times delta x, our acceleration, times our displacement, equals negative V naught squared plus 1/2 V final squared plus 1/2 V naught squared. Here's what I was overlooking. Here's the negative 1, and here's positive 1/2. So when I add those two together, I get the following. Equals 1/2 V1 squared minus, that's where I was getting messed up because we have a negative 1 and a positive 1/2. It's minus 1/2 V naught squared. Great. I'm going to multiply both sides by 2, and we end up with the following. So I was doing everything fine. It's just a wall of math. We have 2a delta x equals V final squared minus V initial squared. I add this over, and we get the following. V final squared equals V initial squared plus 2a delta x. Turns out I was right all along. I just allowed myself to get confused. We end up with the very last of the equations. All right. I'll have one more video after this that I'm going to put together where we're going to do not all 5 of the kinematic equations, but I wanted to show you where these come from. You can get a number of these from calculus relationships, but I usually start off, as we looked at here, I get the first 2 from the calculus relationships, and then I just do algebra after that to find them.